Hey, not Dan here. We are finally live and ready to go and ready to start talking about matter as we get ready for the test coming up. All right, so to start out with, if you guys recall, so since we're talking about matter here, what we're trying to do is be able to classify matter. So there are two categories for matter. We've got pure substances and mixtures. Okay, so if you recall, so pure substances are anything that has a formula. And this is actually a really important thing to keep in mind. A pure substance is something that has a formula, and a mixture does not. Okay, so the whole reason why I specifically bring this up is because what you're going to get on the test is a list of things, and you're supposed to be able to identify it as a pure substance or as a mixture. Okay, so in order to, well, and essentially what you're going to get is stuff like this. Okay, so let's say you know, you're given something like magnesium chloride, and then it'll say MgCl2. We'll have something like iron, and then it'll say Fe. Okay, and then you might have something like dirt, and there won't be anything after it, right? So you're supposed to identify that as a pure substance or as a mixture. Well, magnesium chloride has a formula, so that is a pure substance. Iron has a formula. There's your pure substance. Dirt, and there's nothing, no formula. Therefore, this is a mixture. Okay, so it's actually very simple to be able to identify. Okay, so as long as the item has a formula next to it, then it's going to be a mixture. If there's no formula next to it, well, that is a, I'm sorry, I just said that backwards. My bad. So if it has a formula next to it, there's your pure substance. And then if there's no formula, that is a mixture. Okay. Now, something else that I want to point out here. Pure substances can be broken down into two smaller categories. Those are elements and compounds. Now, how do you tell the difference between an element and a compound? Well, it's actually very simple. You look at how many capital letters are in the formula. So we look at magnesium chloride, MgCl2. Well, it has 1, 2 capital letters. Therefore, this is considered to be a compound. Iron here has only 1 capital letter, so there's your element. Okay. Now, if you are looking at, like, say, a picture, okay, like if you guys remember some of the little cards, you know, that we had to sort out during class. Okay, so magnesium chloride would look something like, you know, you have one shape and then 2 other shapes, but they're going to be overlapping. If it overlaps, that's representing that it's bonded. And then for iron here, like I could have you know, a bunch of squares. They're all the same shape. They're not touching each other, and since they're all the same shape, therefore that's your element. Okay. On the other hand, you've got mixtures. So a mixture would be something like, okay, so if I'm going to draw a square and a circle, okay, and just for good measure, let's put in a rectangle. I know, not the greatest drawing ever, but you know, you get the idea. Okay, so here you have individual atoms, but since they are different shapes and they are not overlapping, so they're not bonded, this is representative of a mixture. Okay, so to quickly kind of sum up everything that I've done so far, we've got pure substances, we've got mixtures. Pure substances have a formula, mixtures do not. Pure substances can be split into elements and compounds. Elements have only 1 capital letter in their formula. and compounds have multiple capital letters in their formula. Now, something else to point out here is that, when it comes to pure substances and mixtures, another way to identify them is by telling whether or not they can be separated. A mixture can be physically separated, whereas a pure substance cannot be physically separated. Okay? So a pure substance requires a reaction in order to split up any of the elements that are there. And then a mixture, well, you can just take that apart, whether it's by boiling or by physically, separating it with your hands. But you can always physically separate a mixture. Okay? And specifically about mixtures, let's go into the 3 different types. Okay? So we have, let me pull this up a little bit more. So the 3 types of mixtures, we have solutions, we have colloids, suspensions. All right, so what's the difference? Okay, well, it's actually very easy to identify the difference. Solutions do not show the Tyndall effect and do not settle out. Okay, now you might be asking, okay, so what exactly is the Tyndall effect? Well, if you remember, the Tyndall effect is that beam of light that you can see in the liquid. So when you shine the light into the liquid, if you can see it, that is the Tyndall effect. Well, for solutions, it doesn't do either, okay? So like if we're talking here, TE for Tyndall effect and SO for settle out, so solutions don't do either one. Now, colloids, on the other hand, colloids will show the Tyndall effect, but will not settle out. Suspensions, on the other hand, show the Tyndall effect, and they also settle out. So anything that you have to shake up and stir up in order to get it to actually get back together, that's a suspension, okay? Any substance that you have in the fridge, right? You pull out the bottle, and on the bottle it says shake well before using. Those are suspensions, okay? So it's actually very easy. If you're just looking at these 2 things, it's very easy to identify what's what, okay? Now, bring this up because on your test on Thursday, you are specifically going to have to identify a mystery unknown mixture. Okay, it's like a little lab practical. So you're going to be called back to the lab tables, and one at a time. You'll be given a little flashlight pen, and you will have to identify what's in that flask as a solution, colloid, or suspension. So when you do that, remember there are 2 things that you're looking for. Your 2-step process. The first thing you look for is, does it settle out? If it does settle out, well, if you look here, suspensions are the only ones that settle out. So if it settles out, there you go, okay? And then you're done. Now, if it does not settle out, that's where you pick up the flashlight pen and you identify it as a solution or a colloid. So you shine the light into it. If you see the light, then that is a colloid. If you do not see the light, that's a solution. Okay? So it's actually very easy. 2 steps to identifying solution, colloid, suspension. Step 1, look for it settling out. If it does, it's a suspension and you're done. If it does not settle out, look for the Tyndall effect. If it shows it, that's a colloid. If it doesn't, it's a solution. Okay? Now, that's doing the lab practical portion of it. If you are wanting to basically identify a solution, colloid, or suspension based on a description, okay, number 1, yeah, you're going to be looking for these kinds of things in the description, but it also might talk about particle size. So when you're talking about particle size, well, I've actually already got it in order from smallest to largest. Solutions are small, colloids are the medium size, and the suspensions are the largest. Now, how do we know that? Well, solutions are the small particles because they're so small that gravity is not able to pull them out, and they're not going to disperse the light, so you're not going to see the Tyndall effect. For colloids, they are the medium-sized particles. So they're large enough to disperse the light and show the Tyndall effect, but they're still small enough to not settle out. Okay, looks like we got a question here. What if the Tyndall effect isn't present in the suspension? Suspensions do show the Tyndall effect. So if you're not seeing the Tyndall effect there, shake it up, stir it up, get all that stuff that's settling out at the bottom, get it all mixed up into the liquid, and boom, it'll start showing that Tyndall effect right away. Okay, all right, so good question. And then last but not least are suspensions, which are the large particles. The large particles, they're large enough for gravity to pull them out, and they're obviously large enough to show the Tyndall effect. Okay, so that's pretty much it as far as, oh, no, my apologies. There is one other thing that we do need to mention when it comes to mixtures before we can move on to the other stuff. There are two other terms, right, that you learned. So that is homogeneous and heterogeneous. You remember that solutions here, these are the homogeneous mixtures. The suspensions are the heterogeneous mixtures. And as far as the colors are concerned, we're not going to ask you about those. Okay, so if we're talking homogeneous, we're talking solutions. If we're talking heterogeneous, that is suspensions. All right, hope that makes sense. Okay, and you guys are welcome to post questions over there on the side in the little chat section. I've got my computer up so I can see it. So any questions you guys have, post them there so I'll be able to respond to those. Otherwise, I'm just going to move on to the next section, which is physical and chemical properties and changes. Okay, we got a question. How do you see the Tyndall effect light? Should it be a straight line? Well, okay. In terms of what you were going to have, then yes, it's going to be a straight line. And the other thing to keep in mind is that the glass itself is also going to reflect some of the light. That's not what you're looking for in terms of seeing the Tyndall effect, okay? So if you're seeing the reflection off of the side or off of the glass, that's not the Tyndall effect. What you want to be looking for is the light in the liquid itself, okay? So but if you check my one of my videos that I have, it's called Solutions, Colloids, and Suspensions, oh my. So if you go and check out that video, you can see specific examples of what that looks like, what it looks like in a solution, what it looks like in a colloid, and what it looks like in a suspension. Because essentially that's what you're going to be given. Do the lights have to be off? No, the lights do not have to be off in order to see the Tyndall effect. Now, yes, it does help, but it's not necessary because obviously for the test we're not turning off the lights while you guys are testing. Okay, but yeah, no, you can totally see it with the lights on because it's a very obvious effect. Okay, this is not going to be something where you're going to look at it and go, I think I see it. Like it's either there or it's not there. Okay, so great questions, everybody. So keep them rolling. Otherwise, I'm going to move on to physical and chemical changes and properties. Okay, so for physical changes and physical properties, essentially what we're looking at here are has the substance changed in any way, shape, or form? Okay, so as far as properties, all you're doing is you're just describing what it is, right? So this substance has a boiling point of 100 degrees Celsius, or this substance measures 5 grams when I, has a mass of 5 grams when I put it on the balance. Okay, those are all physical properties. Physical changes, you're talking about something that has actually changed. The substance itself is still exactly the same. Okay, so if you were looking at the chemical formula of it, it's literally the same thing from beginning to end. Okay, now I'm sorry, I know I'm getting a little ahead of myself by talking about that. So let me backtrack a little bit and go back to the physical properties. So physical properties, remember, are just a description of whatever it is that you are observing. Okay, so we got a question. So Tyndall effect, we will see particles moving around. Yes, you actually will see, because the particles are large enough to be dispersing the light. So yeah, when you see the Tyndall effect, you'll see stuff floating around on the inside. Okay, another good question. All right, so for physical properties, right, they are just descriptions. Two types of physical properties. You've got intensive properties and extensive properties. Okay, so for intensive properties, these are the properties that are inherent to that substance, meaning that it is always the same, it is always true, it doesn't matter where you get your sample, it doesn't matter what you do to the sample, these properties are always going to be true. So these are things like the boiling point, density, melting point, sometimes even like the color of the substance is going to be an intensive property because those are always true. Okay. Okay, so we have a question here. It says, why does freezing water so why is freezing water a physical change? Okay, good question. Because freezing water is going from a liquid to a solid, and that is a phase change, right? So if you have a glass of water, everybody knows that the formula of water is H2O, right? 2 hydrogens, 1 oxygen. You put that glass of water into the freezer and it freezes, it turns into ice. When you pull that out, it's still H2O. Yes, something has changed, right? Something's happened. It's gone from a liquid to a solid, but it is still literally the same molecules. They've just rearranged their shape. Okay? Yes, I do know Mr. Coleman. He's a great guy. So that's why freezing water is considered to be a physical change, because it's still the same substance. Okay? Okay, so what about diameter? Is it intensive? Okay. No. Diameter is an extensive property. Now, why is that? Because extensive properties are measured. They're not always true. They change based on the sample size. So, like, for example, you can take a piece of paper and you can cut a circle, right? And then you can, measure the diameter of that circle. And that's the diameter of that particular piece of paper that you've cut into a circle. So it is a physical property because you are describing what it is. But take another piece of paper. It's the same substance. Cut it into a different size circle. So now it has a different diameter. And now that diameter has changed. It's still a physical property because you are still describing this new circle. But because they're both paper, they're both essentially the same substance on the molecular level, but they have two different diameters. Therefore, that's what makes it extensive, okay? So anything that you can, sorry, I totally lost my train of thought. Anything that you can measure is considered an extensive property, okay? So these are things like length, width, height, diameter, radius, okay? Anything that you can use a ruler to measure. The temperature, the mass, and volume. Now, do not get that confused with boiling point, because you can say that a substance has a temperature of 95 degrees Celsius. Okay, because that means that you measured that substance right then and there, and it was 95 degrees Celsius. But you can get another sample of that same water, and it would be a different temperature. But the boiling point of water is 100 degrees Celsius. And that is true regardless of how much water you have. That is true regardless of what temperature of the water happens to be at that given moment in time, okay? So just because there is a degrees Celsius next to it does not necessarily mean that you just measured it. You got to be careful in reading it. Okay, so things like boiling point, melting point, freezing point, those are all still intensive because those are always true. Okay. All right, why would color be intensive? Well, okay, color is probably not the greatest example to use, but intensive because, you know, if you guys, well, for those of you that are in my class, when I introduced this concept, right, I had the red water, right, because I put food coloring in the water, and then I changed the volume of it, and every time I changed it, it was still red. So therefore, that color would be intensive, okay? When you are moving on to, like if you're doing a change and there's a color change, okay, that's where you got to start thinking about, but again, those are changes and not properties. So do your best to not get those two mixed up, okay? Is that shirt available online? You mean the shirt I'm wearing right now or my Not Dan shirt? Because I have Not Dan shirts, and those are available for purchase online on my website. But this, no. You have been subscribed to me since 2006. Well, that's quite impressive feat. I just started this last year, so. But good to see you again, Nintendo Man 01. I remember from last year. All right. If you can't turn a substance to its original state, so it's chemical change. And if you can, it's physical. Okay. All right. So that is a very good question to ask because that is a common misconception. That's not necessarily the best way to think about physical changes versus chemical changes. Oh my dear goodness, there's France. France has made an appearance. What's going on, man? All right. So, dude, you got me all, you got me sidetracked. Okay. Because, okay, so a lot of ways that you can think is like, okay, so if I've changed it into something new and I can't return it back to its original state, therefore it must be a chemical change, which is true if you're burning something like what we did in the lab. You burn magnesium and it was now ash. It is completely different and you are not going back to the way it was before. I can take an orange. I can slice it in half. I just changed it. And I'm not fusing it back together. I do not have the ability to fuse the orange slices back together. So I can't return it to its original state. But it's still an orange. And I didn't really do anything to it other than cut it in half. So you can't use that logic when trying to identify if something is physical or chemical. So what you really need to do, the best thing to do, is to try to look at it from a formula standpoint. You got to think, is this substance the same or is it different? If there's a change that has happened, but it's still the same substance, that is a physical change. But if a change happens and now it is something different, now that is your chemical change. Okay? All right. You're a very intelligent guy. To meet my brother is going to start a channel. Any tips? You know what? If you have any any of those questions, feel free to ask that on some of my other videos because I want to keep this focused on the review for the test. But or you know, if you want to just stop by my my classroom and we can talk anytime. Cool. All right. Okay, so that's actually really just about everything I think when you really get down to it, because we talked about the pure substances versus mixtures, and then solutions, colloids, and suspensions, homogeneous and heterogeneous. Okay, so know all those vocab terms. Okay, and then we just talked about it's all good. It's all good, friends. Check you later, man. All right. Would squeezing an orange be a physical or chemical change? And what about souring milk? Okay, so for souring milk, you have an odor change. And why is there an odor change? Well, because the milk has turned, right? That's typically the phrase that people say, the milk has turned. And it starts getting chunky, it starts curdling. Yeah, that's not the same substance anymore. So that would be considered a, a chemical change, right? So souring milk is chemical. Squeezing an orange. So squeezing an orange is a physical change. It's a physical change because, yes, something has happened and you've changed it, but it's still all the same substance, okay? Yeah, you separated the juice from the, the outer skin part of it, but chemically, it's all still the same thing. So that's another example where you can't exactly say, well, because I can't return it to its original state, therefore it must be chemical, because that's not really the best way to think about it. You have to think what's happening to it, happening to the atoms. If the atoms are being rearranged in any way, shape, or form into another substance, that's chemical. But if the atoms are essentially staying together, if the bond is still there, that is a physical change. Okay? All right, so when is the test? The test is going to be this Thursday. And how many questions are on the test? Hey, look, everybody. We have our first our first troll. And for that, we say bye-bye. Okay. All right, so how many questions are on the test? I have to go back and take a look at it again, so I will let you guys know in class tomorrow. But if I remember correctly, 25 multiple choice questions, and they are 3 points each. So that gives you 75 points on the Scantron. And there's also going to be a free response section. And on the free response section, there's like 3 or 4 questions there. And those will add up to 25 points each. Okay, but we'll talk more about that tomorrow in the actual, the official review session. All right, what about water freezes to make ice? Okay, I think I believe I said that before, but so water freezing is a phase change. All phase changes are physical changes, okay? Yes, Meme Master, I can give you a shout out. There you go. You got a shout out on my channel. All right, what is the first thing I look at to tell the difference between a physical and chemical change? Okay, it kind of depends on the way the question is worded, so you have to read it carefully. So obviously the first thing is read it, okay? Don't just kind of read the first word and the last word and assume you know what all the other words in the middle are. You have to read the whole thing. So the main thing to look at is, has the substance turned into something new? If you have made something new, so like if you see a word like reacted, a word like to create or created, anything that means essentially that is a dead giveaway that it is a chemical change. If you're making something new, like if you see the word form, okay, like for example, in the lab that we did, right, the demo, the teacher demo, the magnesium got put into the sulfuric acid and it formed hydrogen gas. That's a dead giveaway that is a chemical change. But if you remember also from the lab, there was that one station where you put the salt into the water and you dissolved it and it looked like the salt disappeared, but then you boiled the water away and the salt was left behind. It was still the same thing. You still had H2O, you still had NaCl. It was literally the same thing, and therefore that is a physical change, okay? Where am I in school? My room is S207, and you're always welcome to come chat with me anytime before or after school, S207. All right. Okay, so that's pretty much everything. So I'm going to start wrapping up here. So I'm going to give you guys a couple more minutes to type in whatever questions that you guys have. Let me know what questions you've got. Otherwise, I'm just going to start wrapping this up, and I'm going to take a sip of my homemade blueberry soda. Oh yes, recipe courtesy of Alton Brown from Good Eats. Oh yes, I highly recommend it. All right, so do you guys have any other questions? Just kind of hanging out at the moment. If I don't see anything in the next couple of minutes, because I know there's a little bit of delay between when I say it and when you see it on the screen. Okay. What if the water catches on fire? Then you got a serious problem if water is catching on fire. Because if water is catching on fire, that's not the water that's on fire. It's most likely because you have oil floating on top of the water, and it's the oil that's on fire. And you got a serious problem. So put out the fire. So I don't know what that's all about. Why is crumbling paper a chemical change? It's not, actually. Crumbling paper is a physical change. And yes, I know why you're asking that, because that's on that little test review packet. That's a trick question. It's there to see if you're paying attention. So crumbling paper is not a chemical change. It is a physical change, because yeah, it's still just paper, right? Nothing really happened to it. You just changed its shape. Okay? So all great questions. Anything else? Just hanging out here online, enjoying some company, the good company of all you lovely people out there in YouTube land. What if you burn the paper? Okay, good question. If you are burning anything, chemical change, because burning alters the chemical makeup of that substance and it turns it into something new. Okay, so burning paper, all that burning magnesium, burning copper, burning anything, that's a chemical change. All right, is oxygen combines with iron to make rust a physical change? Okay, that is a good question. When you look at that question, okay, look at the word combines with. That essentially means you're reacting, and it says to make rust. You are making something new. Therefore, chemical change. Okay, great question. Any other questions? When's the next live stream? Well, at the moment, it's not scheduled yet. I can't guarantee that I'll be able to do one of these live streams for every test, but that's kind of the idea here. And so our next test isn't going to be for another couple of weeks. So we got time. Okay, so I will definitely let you guys know. All right. France, no, you don't have to take the test. You're not accepted anymore. Non-Newtonian fluids like oobleck is physical, right? Yes, and okay, so yeah, when you make a non-Newtonian fluid, like if you put cornstarch and water, you are making a mixture. So yes, that would be a physical change. Good job. You remembered something from chemistry last year. Now focus on physics. All right. Any other chemistry questions? I don't know. I'm just just hanging out. Since what year have I worn glasses? Since my junior year of high school, so that would be the fall of '96, so 20 years ago. Wow. So yeah, so it is officially the 20-year anniversary of me wearing glasses. And there you go. All right, what are egg whites? Okay, so egg whites are colloids, and that's probably not the best example for us to have put on the test review now that I think about it, simply because, okay, well, mainly because it's a colloid. The only time we're really going to ask you about colloids actually is when we're but like when you're having to identify solution colloid suspension from the flask. So don't worry so much about those egg whites. The blueberry soda is absolutely delicious. Yes, I made it myself. It's greatness. All right, what is the Tyndall effect most useful for? Okay, So the Tyndall effect is most useful for identifying between or distinguishing between a solution and a colloid. Now, why is that? Well, because you don't need it to identify a suspension. The suspension is the only one that settles out. So that is supremely easy to identify, meaning that the harder ones to identify or distinguish is the solution and colloid. And how do you do that? With the Tyndall effect. Okay, great question. Okay, is blueberry soda chemical or physical? That would be a physical change because it is a mixture. Okay, I took the blueberries, I crushed them, or actually I boiled them first, added in some sugar, squeezed out all the juice, and then I mixed in some seltzer water. So there you go. It's all a giant mixture, which is a physical change. Okay. All right. Yes, France, you are distracting again. It's all good. Is heat work with chemical change or physical? Okay, so that's another great question. Sorry, I'm getting distracted here. You have to pay attention to what the question is saying when you're talking about about how heat is involved. If it's talking about boiling something or just heating it up, that's all physical because you're not changing the substance. But if you're talking about heat in terms of heat is being produced from a reaction, case in point, the magnesium and sulfuric acid that we did as the teacher demo in the lab, it produced a lot of heat. So the heat was coming as a direct result from the reaction, and that's chemical. Also, if you're talking about heat as in terms of like it's on fire, it's burning, that's chemical. Okay, so if you're just talking about phase changes and just changing the temperature and having it go up and down, that's physical. But if you're talking about heat in terms of it making something new or burning something or as a result of a reaction, that's a chemical change. Okay, and you're welcome for the recipe. Actually, all you got to do is just search blueberry soda, Alton Brown, and there it comes. There it is. All right. So what are the examples of solutions? Okay, so examples of solutions are things like salt water, Kool-Aid with food coloring in it, orange juice without pulp. But if you have orange juice with pulp, well, now you have a suspension, right? Because the pulp settles down, you got to mix it up in order to get the pulp to get in there. But if there's no pulp, orange juice without pulp, there is a solution. Why is okay? So Patrick, you're asking to explain solution, colloid, and suspension. I actually did earlier in the video. So if what you'll do is just either scroll back, or you can find one of my other videos that I've already posted, which is called Solutions, Colloids, and Suspensions, oh my, and then part 2, which is called Not Dan and the Mixtures, part 2. I go into a whole bunch of detail on those, or you can just scroll back in this live stream because I talked about that at the beginning. Okay, why is orange juice not a pure substance? Well, because orange juice is can be separated, right? Because you got the orange stuff and essentially water. Right, because you can boil it and the water goes away and you're left with the rest of the orange, whatever makes up the citric acid and the various other things. It is actually a mixture. So yeah, you can have pure orange juice, but it's still a mixture. Okay, a pure substance has to be an element or a compound, and an element has to be found on the periodic table of elements, right? And there's no square in the periodic table for OJ. Okay? It doesn't work like that. And you also can't take any of the stuff on the periodic table, put it together to make a compound that we then call orange juice, right? There's no formula for orange juice. And because there's no formula, there's your mixture. Okay? All right. The t-shirt link is actually found on my music website, which is roadsidebeggarsmusic.com. Here, let me type that in if I can do that. So typing it in right now, roadsidebeggarsmusic.com. So there you go. That's the t-shirt link, and you'll scroll to the projects page. So you go to the main website, go to projects, and then scroll down, and you'll see information about the t-shirts. Okay. Am I keeping last year's videos for this year? Of course I am. I'm not going to redo all of that. That was a lot of work. All right. So any other questions? Okay, we're about 40 minutes in. Any other questions? Yes. So Patrick, here is your shout out. You are receiving a shout out on the official Chemistry Talk with Dan YouTube channel. There you go. All right. Italian salad dressing. Okay. Italian salad dressing is a suspension, not a solution. Now, how do I know that? Because on the bottle it says shake well before using. Right? Have you ever picked up a bottle of Italian salad dressing? Right? You can see all of the, because there's a lot of solid stuff in there, right? There's vinegar and there's oil, and then there's like solid particles that are in it, like all the like. I'm sorry, I don't know the exact recipe, but they all settle out at the bottom. And you have to shake it up before you can then pour it out in your salad. Right? Italian salad dressing is a sorry, I lost my train of thought. It's a suspension. Okay, so another good question. All right, anything else? Anything else? I'm just hanging out here, just chatting. Cool. If you want to switch, well, I can't endorse that, so don't quote me on that. But you can always catch me here on YouTube, even if you're not successful in switching out. Okay. All right. So I'm going to give you guys another minute or so to come up with any other questions, and then I'm going to sign off because I want to have my evening. So. Anything else? As I take my last sip of my blueberry soda. Sorry, I know, I'm a nerd. It's what I do. All right. Thanks for the help. You're welcome for the help. Isn't Kool-Aid a suspension? Kool-Aid is a solution because it's just sugar water. You take the sugar packet, you put it in the water, you stir it up, nothing is settling out. Now, the only reason why Kool-Aid might settle out is because like if you put too much in there, right? If you don't have enough water, you just put a whole bunch of the Kool-Aid stuff in there, the sugar packet, and then, yeah, you'll see something settle out, but it's more like sludge. That's not like true settling out, and that's only because you put too much in there. But if you put the right amount, it stirs up, and you don't see anything settle out. It all completely dissolves, so it's a solution. Okay. Do I still respond to last year's videos? Of course I do. Yeah, if you want to make comments on the videos, I still respond. Okay. Is malleability intensive or extensive? Excellent question. Malleability is intensive because it does not matter how much of that metal. So like copper wire is very malleable. And by the way, in case you didn't know, malleability means that it's able to be bent, right? You can change the shape of it. So I can take copper wire and I can bend it and turn it into a different shape. That is an intensive physical property because it doesn't matter what I do with it. I can cut it off and I can still change the shape, or I can get me a long piece and turn it and shape it. It's always going to be malleable. That's just something about it. Plus, I can't measure the malleability of a metal. Well, okay, I'm sure you can if you get into metallurgy and you're like, you're studying to be like a engineer, or something like that. But as far as this class is concerned, yeah, we don't have equipment that can just measure the malleability, so therefore, intensive property. Okay. Why is heat? Okay, hold on. I'm trying to read some of a bunch of questions showed up all at once. Why is heat required to melt ice? Is it okay? So when you heat up ice and you melt it, that's a phase change and a physical change. Phase, physical, pH, same thing. Okay, so that's why it's just a physical change. It's not chemical. It's still H2O. H2O in ice format just takes a different shape than H2O in liquid format. Okay, but it's still H2O, physical change. You finished your IRP. When can you turn it in? I don't know. I don't teach honors chemistry, so yeah, we don't deal with IRPs. So you'll have to talk to your own teacher about that. Okay, why is white tea lemonade a solution? Again, probably not the greatest example for us to put on the test review. White tea lemonade is like when you mix it all up, there's nothing really settling out at the bottom. And it's also like the particles are just so small that you're not really seeing anything. But that being said, don't worry about that specific example because we're not going to get that detailed on the test. Okay, the examples that we're going to give you on the test are going to be stuff that you're very familiar with, and you should know what they are. Okay, so don't worry about that. Tell me, Coleman, he is lit. Well, of course he is. Mr. Coleman's an awesome guy. I highly respect him. He's great. Okay. Do I teach? I teach on-level chemistry. Yeah, that's right. I teach on-level chemistry and video game design, which you should sign up for second semester. It's a semester-long course. But yeah. All right. How would a physical and chemical look when drawn? I'm not really sure what you mean by that. How would a physical change, like talking about like properties when they're drawn? You're not going to have to draw anything on the test, and the only images that you're going to have to interpret are the solutions, colloids, suspensions, or like pure substance versus mixture. Like there's those series of questions on the front side of the learning guide in the multiple choice section. That's pretty much it. I'm not going to ask you to interpret a drawing of a physical or chemical change. Okay. France, don't you have something better to do with your life than watch one of my live streams? You're asking stuff that we're not going to get to second semester, and I don't want to confuse everybody else. Dude, you crack me up. All right. Yeah, what's plasma? Plasma is a specific phase. Like everybody knows solid, liquid, and gas. Well, there's a secret fourth phase or state of matter called plasma, which we may or may not get to because that's not really part of this course. So don't worry about that. Okay? So I know the bar for exciting YouTube has been raised by you watching me drink my blueberry soda. All right. It's all good, friends. You're up, dude. Okay. All right, so I think that's about it. Most of the questions you guys are asking now are just literally straight from the test review packet. So I'm going to sign off at this point. So any further questions you have, we will take care of in class tomorrow. So I appreciate all of you guys signing in and watching this first of the school year. You guys are awesome. You're why I do this. Otherwise, I'd just be sitting here talking to my webcam in my all by my lonesome. So I'm going to sign off. Thank you guys so much. You guys rock. I'm not Dan, and neither are you. Check you later, everybody.